All right, let's go ahead and get back into it. So we briefly got into section 6.2 yesterday. I just wanted to hit the title again because I don't think I talked about it. Or I don't think I mentioned it. But this Gram-Schmidt process is essentially what we did yesterday. So this is basically it's this iterative process that allows you to take any old basis of a subspace and replace it with a basis of the same subspace whose vectors were orthogonal to each other. So we did this yesterday with this basis concerning just two vectors. But yeah, that's what Gram-Schmidt is. So basically, it's this process we go through to construct an orthogonal basis. So if you're given a basis, basically the way it's written is you take one of the vectors as, you just take it and accept it as is. And then the way you construct the other vectors, or the next vector, is to basically find this part of it, which is, the majority of our work yesterday was to figure out the part of vector V2 that was parallel to U1. Once you identify that, you can subtract it off of V2. And that gives you something, that gives you this U2, which is orthogonal to U1. You can generalize this even further. If you need more vectors, so let's say we need a third vector, then you got to find a vector that removes the component that's parallel to U1 and the component that's parallel to U2. So basically, if the more vectors you need, the more things you have to essentially dodge. There are more vectors that you've already built that you have to remain orthogonal with. So that's why the first vector is very easy. There's no problem with one vector. The second problem, you have to avoid sharing any directions with the previous vector. If you have the third vector, there's two vectors you have to avoid sharing directions with, and so on. So that's basically that's this algorithm. This is this process for, there are many ways to replace a basis with something orthogonal. This one it's surefire. It will always work. So any questions kind of on, like, we've done one simple example with this. Now we're kind of formalizing it. Any questions so far about kind of the rationale behind it? All right, so let's do one with a third vector in it. So I want to find W is this subspace, this portion of R4 spanned by these three vectors. But these vectors are not orthogonal to each other. They're not pairwise orthogonal. So I'd like to replace it with something that is. There's no real reason to call the very first thing I wrote U1. We just have to pick one. So to illustrate that, which one do you want to start with? The third one? Okay. So we'll say U1 is equal to, so -16, -2, 55, 31. So we know, one thing we talked about a couple weeks ago is that a basis is not a unique thing, but the dimension of it is. So if I replace this with another basis, that basis has to have three vectors. It has to have exactly three vectors. So we get one for free. We can just choose one from the original basis and start from there. What vector would you work with next? So we already kind of dealt with this one. I'm gonna go vector 1 or vector 2. Vector 1 sounds good. Okay. So let's do this. I've drawn this like little schematic diagram a bunch of times, but just to kind of remind you what we're doing here. So this vector down here on the bottom, this is, I'm going to call this V2. And I'm going to call this one right here U1. So these are not orthogonal. So what I'm trying to do here, the first thing I need to find is I need to find this piece right here. I'll call these things X and Y. But X is the part of U1 that's parallel to V2, that has the same direction. Y is the part of U1 that is fully orthogonal to V2. So I'm trying to make that decomposition. So what's the way we do that? So we're trying to find an orthogonal projection. We can use that. We can do that with using dot products. So U1.V2. So this dot product base will give me, it'll give me a sense of how much directionality do U1 and V2 have in common. But that's really only valuable if I give it as a ratio of the length of U2 or the length of V2. And something we talked about yesterday, if you dot a vector with itself, it gives you the square of its magnitude. So this right here is going to give us like a proportion of the vector I want. But the thing I want is going to be in the direction of V2. So I'm going to multiply this ratio by V2. So this thing right here is called the orthogonal projection. You know, we did a lot of these yesterday, but it was toward a different objective. So I just want to point out that the calculation is very similar to what we've done. We're using it to do something slightly different. We're focusing on something slightly different. All right, so what are these dot products? I got 97, 97.49? Yes. Oh, that's almost convenient. Check it again, because when I did this, I got 98 over 49, which would be very nice. I also didn't do the vectors in this order. U1.V2. I don't know what 16 times 17 is. For the denominator, I got negative 378. So let's go through it slowly. So let's make sure we're looking at the right things here. U1 is this. V2 is the second vector I was given, as is. So 16 times 17, negative 272, plus 28, plus 55, minus whatever 31 times 6 is, 186. And then V2.V2, 17 times 17, 289 plus 156 plus 1 plus 36. I believe that's all okay now. So for the denominator, I'm getting 482. And I already forgot what I told you for the other one. 275? Okay. I got negative 374. Someone corroborate one of us. Okay. Cool. So do I now. All right. So this is the terrible, terrible ratio we got right here. Does this reduce at all? That'd be too easy, right? I'm just gonna leave it. So that's the ratio we got. Excellent. I'm on roll today. Okay. That reduces. What'd you get? Okay. That's a little better. All right. So now that we've got that number, what did that actually do for us? What did we find out? Right. So this right here, this thing that I called X earlier, I think I can say this. This is negative 125 over 174 times V2. So the goal I have right now is to figure out what our new vector 2 is, the vector 2 that we're going to use for our orthogonal basis. So how do we get that now? How are x, y, and u1 related in this triangle? So something we talked about briefly yesterday was this idea of like vector addition. If you're looking at a diagram of vectors like this, we can add them tail to tip. So since, if I go from the beginning of x to the end of x, which is also the beginning of y, then I follow to the end of y, that better be the same. Adding those two vectors together needs to be the same as u1. So x plus y equals u1. u1 I know. Y is the thing I really care about because it's orthogonal to v2. And x is the thing I just learned, right? I think I lied to you all again. I think I made the same mistake I made yesterday. I don't want something orthogonal to v2. I want something orthogonal to u1. So let's take a dot product that we actually care about. Right, because now if I find y will be perpendicular to u1, which is what I want. Okay, so what's u1 dot u1? 9 plus 36 plus 0 plus 4. Is there any chance this is friendlier? Thank you. I'm on fire today. Who wants to take over? All right, 16 squared is 256 plus 4 plus no idea.
Or be correct, would it just be easy to just pick that?
Yeah, I mean, you can pick whatever you want as long as you don't lose sight of what you chose, like I keep doing. But yeah, it might be easier to just go in order. But concretely, it doesn't really matter. I think the thing that hurt me was that I called it u1, so I keep looking at that first vector. Did I even find the right dot product in the numerator? U1 dot V2. 16 times 17. Yeah, that's fine. Okay, so negative 375 over what's this actual denominator? 4246. Good, good. So now I have found the portion of V2 that is parallel to U1. But the thing I really want is the portion of V2, which is fully perpendicular to U1. So the way we're going to calculate that is this. U2 is equal to U1 minus that doesn't seem right. What am I doing wrong? Oh, V2. So if x plus y equals V2, the thing I really want is y. So if I isolate y here, I get y equals V2 minus x. So this right here should give me U2. Will anyone's feelings be hurt if we went straight to, if we just did decimal approximations from now on? Or do you like that nasty fraction? So 17, negative 14, 1, negative 6, plus 375 over 42, 46, U1, which is negative 16, negative 2, 55, 31. Okay. Any disagreements about what I have for U2? Positive? Yeah, that would make sense. Okay. All right, so what did we just find? What's special about this vector U2?
Now let's find U3.
Well, yes, but like so far, like how are U1 and U2 related? They're orthogonal to each other. So I have to build one more thing to make this basis. But the way we stack that up is going to be essentially the way that we did this last iteration. So now the only thing we have to worry about is that there are two vectors we have to get away from now. So U3 is going to be equal to V3 minus those two parallel directions we have to worry about. So how do we find those parallel directions? Well, we can kind of use what we looked for before as reference. So this right here helped us find the part of V2 that was parallel to U1. I want to do the same thing, but with V3. So I'm going to do U1 dot V3 over U1 dot U1. And that'll be in the direction of U1. So I want to avoid the part of the vector V3 that shares directionality with U1. But doing that alone will not, that'll make this thing perpendicular to U1. It won't make it perpendicular to U2. So I have to do a similar subtraction with respect to U2. So I want to find the part of V3 that's parallel to U2. And remove that as well. So before we actually like go through the calculation and get the vector, ask me all the questions you have about why that's the calculation to make. Why am I subtracting those things off? Are we okay with the rationale there? Okay. So now we can plug in all the details. What is V3? It's actually the one that we wrote down. Yeah, the furthest left one. And then U1 dot V3 U2 dotted with itself would be awful. All right.
How come you can't? How come you can't make the multiply by get out?
V3, which are we going to the bottom equation here?
Yeah, I need.
So it's a matter of there's a couple things. One is what my objective is. The other is what kind of actually it's mostly that. Actually, I don't know if I could cancel anything. So these are not like true. This is not like a traditional multiplication. So because of that, this cancellation isn't really something that works. So that's one side of it is that the cancellation doesn't work in the way, I'm sure you've seen this example and other things. If you have something like 3 plus 7 over 7, that cancellation doesn't work, right? So the reason that cancellation doesn't work is because how are 3 and 7 related in the margin there? Like what operation am I doing on them? That's addition. And canceling is inherently an act of division, which is not the opposite of addition. So for the same kind of reason here, this right here is going to be a scalar. So this is a scalar multiplied by a vector, which is not the opposite of the product that a dot product is. So because of that, it looks like there's cancellations available there, but there's not really. All right, this dot product is, I'm getting 489-ish. What was I doing? Oh yeah, never mind. Minus that times U1, which is one of our original three. Minus something else over 488.9. No, it's not. Wrong vector. Why do I have different values for U1 dot U1?
U2 to U2.
I should have just stuck with it as an order. I'm all over the map. So this first one right here, I'm positive this is a fine way to go. I keep losing sight of what belongs to what. So V3 is actually this, right? And then we called this first one U1 or V1. And this right here was V2, right? So let's make sure I'm actually assigning the right things in the right way. So V3 is this minus U1 dot V3 in the numerator. Yeah, that's definitely not 98. I did the wrong thing. So minus 50 over 4246 times U1. And I think U2 dot U2 is the thing I already did, which is the 488.9. So I think the last thing we need is whatever U2 dot V3 is. So again, this right here is U2. V3 is the very first thing we looked at. Times U2, which is are people okay with this fraction right here?
Yeah, fine.
Awesome. So we have an orthogonal basis. It's not very pretty. I mean, one of them is the vector we ended up with. So I'll box into the things we actually want to keep. U1, U2, and then I'm going to save us the pain of actually consolidating that, but that's U3 right there. So obviously you're under no obligation to get friendly looking results from this, but I want to make sure, are we okay with the way this goes? Kind of the process we followed to get here. Any questions? All right. Let's do another one. This time I'm mandating that whatever vectors we come up with have integer quantities in the entries in the vectors. So let's try not to be clever this time and just go in order. So I'm going to require that u1 is equal to -3, -3, 0, 0. And kind of in general, the names I'm using, the things that were given, the basis vectors were given, I'm assigning those these. And the new vectors we're getting, I'm calling them u, just kind of arbitrarily, just to keep them organized. So I'm going to take u1 as equal to v1. How do I build u2?
U2, I guess. Or U1 times V2, all over U1. And then kind of another U.
Okay, so that's, I do need that, but only because I want to get rid of that. So I want to find out what part of u1 shares a direction with v2 in proportion to how long u1 is. And then I want this to be in the same direction as u1. So I'm going to multiply this thing right here that'll be a scalar. I'm going to multiply it by u1. But like I said, that's the thing I want to get rid of. So what am I subtracting that from? V2. So basically what I'm doing here is this. I have a vector u1, and I'm trying to break down vector v2 into two pieces. The part that's parallel to u1 and the part that's perpendicular to u1. So I know exactly what v2 is. It's given to me. I know exactly what u1 is. I defined it based on what v1 was. So if I find this third piece, this difference will give me what I want. So v2, I'll just rewrite 0, 1, -3, 0. And we'll find some dot products. What is u1 dot v2? It's just -3, right? Minus -3 over whatever u1 dot u1 is. 18. So plus 3/18 of -3, -3, 0, 0. So if I evaluate this whole thing, 3 over 18 is 1 over 6, right? 1 over 6. So I get 0 plus -3 over 6, -1/2. 1 minus 1/2. So 1/2. -3 plus 0. And 0 plus 0, right? So that would be a good vector u2, except for I laid down this new requirement. So I want my vectors only to have integer entries. So, but I know this is the direction I want. So how could I fulfill that requirement? Multiply everything by 2. So if I multiply a vector by a scalar, I preserve the direction. So -1, 1, -6, 0 is fine. Is this perpendicular to u1? A lot easier to see when when I have integers involved. So yeah, that dot product is 0. Okay, so if that's what my u2 is, I need a third vector. How do I get that? If we got to be specific because there's so many vectors now.
2 times V
U2 dot V3.
all over U 2 times V2.
Hmm.
Times V2.
Yep.
Check 1. One times V1.
Good. So I want all the I want the information of V3. So I want the information that's in U3 that doesn't share any directionality with U2 or U1. So that's why I'm subtracting these things off. So what is V3? 0, -3, 1, -3. Minus, we have not done this. What is U2 dot V3? -1 times 0 is 0. 1 times -3. -6 times 1. I'm getting -9 over U2 dot U2. So 1 plus 1 plus 56. U1 dot U1 is still 18. All right, I'll stop there. Double check me. I don't like that first fraction, but I think it's what it has to be.
I got a -9.
Right, but I'm subtracting. So I just consolidate. So I'm subtracting it. So I consolidate the negative signs. 9 and 38 don't reduce. Awesome. So we want to get a vector in the end here that has only integer entries. So I have a couple choices. Do we want to force all these things to be integers now, or add them all together and figure that out at the end? Okay, sounds good. So then this first entry is going to be -9 over 38 plus 3 over 2. Then -3 plus 9 over 38 plus 3 over 2. And then 1 minus 54 over 38. And okay, I get one for free. So that's a vector that contains the directionality I want, but it doesn't contain integers. How can I get integers out of it? If I convert into decimals, I worry about what the rounding will do to the information I'm trying to hold on to. So notice what we did to get U2. So I found this vector right here, which his directions are good, but I don't like the fact that it has fractions in it. So what did we do to this vector to get our real U2? We doubled everything, right? Is there a similar scaling I can do to solve the same problem here? What are the denominators I have to worry about? 38 and 2. So what can I multiply by to get integers from there? I could do 76. That would definitely work. 38 also works. since 38 is even, it'll cover the things that are halves as well. All right, so if I multiply everything by 38, what do I get? I get -9 plus 3 times 19, -3 times 38, plus 9 plus 3 times 19, 38 minus 54, and -3 times 38. -57 minus 9, 48. All right, I believe that's where we ended up. How are we doing? Do we agree with my U3?
Yes.
Okay, so U1 and U2. And then our last one. So still got something orthogonal. We could verify it if you want, but we also have only integers. So hopefully these are nicer to deal with than whatever we just came up with. Questions so far? All right. So next thing I want to do is find an orthogonal basis of W with vectors of length 1. So I know for a fact that if you go through this in the order that it's written, it comes out real convenient. So I'm sorry, but I'm going to make us do that. I did not foresee it getting as hairy as it did before. So let's do this. U1 equals vector 1. We can fast forward a little bit, which means that U2 is going to be equal to V2 minus V2 dot U1 over U1 dot U1 times U1. I believe that fraction comes out to something. So -135, -147. I believe that's just -3, right? Okay. That's a much better looking U2. Unless you disagree. I think 8410 is what I got before though. So to get U3, starting with V3, I'll subtract off all the parallel pieces. So V3.U1 over U1.U1. +64 plus 16. All right, let me take a pause, make sure that I'll give you time to catch up and find all my mistakes. Convenient. Even more convenient. Any questions or corrections before we go on? But I think we got U1. Yeah, U1 is basically given. U2, we found quickly. U3, the further you go, the longer it's going to take. But I think now we can kind of put the pieces together and get U3. So 98 over 49, that's 2. Negative 81 over 81, that's +1. So if I do this operation, I should be able to get U3. So negative 16 plus 6 plus 8. Negative 2. Negative 2 minus 12 plus 4 minus 10. 55 plus 1, 56. And then 31 minus 4 is 27. Okay. So now we have another orthogonal basis for this span. But the requirement I'm giving now is I want to find vectors that are only 1 unit long. Have we talked about how to find how long a vector is or what the magnitude of a vector is? How do we do it? So how would I find out how long U1 is?
Square root all of them, but first you square them again.
Yeah. So basically it's Pythagorean theorem. Pythagorean theorem can be done in any number of dimensions. So if I want to find the length of U1, it's equal to the square root of -3 squared plus 6 squared plus 0 squared plus 2 squared, which is the square root of 49. Oh, that's easy. 7. Okay. And I can do the same thing for U2 and U3. So let's do that as well. I think U2 is also convenient. The square root of 64 plus 16 plus 1, which is the square root of 81, or 9. And then U3, I would feel shocked if it came out to be nice. This comes up to actually 63. Oh, never mind. So clearly I don't have what I want because all these vectors they're longer than 1. But can I replace U1, U2, and U3 with vectors that are 1 unit long? How would I do that? So right now, U1 is 7 units long. I could basically divide all these vectors by their own length. So U1, and just for quickness, I'm going to write it like this. U1 equals 1/7 of -3602. U2 is equal to 1/9 of 8, 4, 1, and 0. And then U3 is equal to a 63rd. Of -2, -10, 56, 27. So now we have an orthogonal basis that has another property. All the vectors are exactly 1 unit long. They're called unit vectors. So any questions on how we made this base? I mean, we've made a few different orthogonal bases now. This process right here is called normalization, where you take all the vectors, or when you normalize a vector when you keep its direction and you reduce its length, or reduce or amplify its length to 1. Questions? All right, so a phrase you'll see in the homework and hear for the first time probably is the word orthonormal. So this is a combination of 2 different characteristics. It's orthogonal and all the vectors are normal, which means they all have a magnitude of 1. How are we doing? I have one more example here. Do you feel like you need it? Should we do it? Or are we experts on Gram-Schmidt? Think you're experts? Okay, I'll believe you. So we did one of my examples twice. Let's bail out. Okay. So moving on to 6.3. Which is essentially is an alternate way to figure out or to find orthogonal projections. So a question I've asked a couple times now in a couple different sections. So if W is some subspace, of course it isn't. Yeah, that's right. I learned how to use this thing. All right, cool. So if W is some subspace, V is some random, like arbitrary vector, probably doesn't belong to this span. I mean, how have we been finding these things? So basically, I've been calling this vector right here like by the name of it, like just as a vector, but now I'm gonna just call it W. I'm gonna let this one vector represent the entire subspace that's spanned by all the things in its basis, all the vectors in its basis. And I want to find the vector W, or the vector in W, which is closest to V. Is this something we know how to do? Okay, so we've, in a few different contexts, we've talked about how to do this. So let's bring another way to do it. So I'm going to let A be some basis, and it's ordered. So I say I don't want to move these vectors around. I'm going to let U just be some random vector, probably not in my span, not necessarily in my span. And I want P to be a vector that most closely resembles U, but P is actually in the span of A. One more thing I want to introduce here is that I'm going to say let C be a coordinate vector. So, and specifically the coordinate vector that makes this true. If I multiply A by C, I get P. So basically, C is the thing that defines exactly what linear combination of the vectors in A yield P. So these are all the different things. I'll try to draw, my standard picture. I'm going to call this vector now. Actually, I'll kind of looking forward here. What I eventually want to do is scale up from a single vector into a full matrix. But to start, let's just talk about single vectors. So I'm going to call this vector P. It's in the span of A. There's this vector U that probably isn't. Doesn't need to be. And I'm going to just call this other thing K. This is basically that orthogonal piece. So based on the way these vectors are related, what can I say about this dot product, P dot K? What's that? Doesn't equal U, because so U is a vector. If I dot two vectors together, I always get a scalar back. It's not the magnitude of U. If we look at the diagram, I mean for that to be a right angle. So if those two vectors meet at a right angle, then what do we know about their dot product? It equals 0. So that is a few seconds ago. I know it was one of the first questions I asked, but I asked it exactly in the opposite direction. How do you tell if two vectors are perpendicular or orthogonal? By definition, their dot product is 0. So now that I'm guaranteeing you these two vectors are orthogonal, then I know I get this dot product for free. So let's start dropping in some other things here. So let's solve for K. I know that P plus K equals U. So what does K equal? K equals U minus P. So that's one way. That's the first way that I'm going to rewrite this here. I know that P dot U minus P is equal to 0. But P is just a combination of all the things in A, right? So what I'm going to do is this. I'm going to replace P with any one of those vectors. I'm going to just say VI. Basically, this is just the generic vector in that span, right? And do I want to leave this P or VI? Yeah. Actually, that's not quite right. P is not equal to V. P is equal to A times V. So the next thing I'm going to do here is going to be kind of cheating, but it's not. I promise. So I'm doing dot products, right? Dot products always give me a scalar answer. I would love it if there was a similar operation I could do that would give me not 0 the scalar, but 0 the vector. So when I do dot products, that always gives me a scalar. But am I allowed to multiply? For example, am I allowed to do VI times U? No. Why not? Why is that bad? Well, I could dot them together, but can I multiply? So I can dot them together, which is like a special way to multiply vectors. Am I allowed to multiply them in the way we multiply matrices together?
No.
Why not? What are the dimensions of V1 and U? They actually do have the same dimensions, just that doesn't help. So their dimension is basically the order of both of these things is n by 1 because they have n rows in one single column. So it'd be nice if I could replace VI with something like VI that I could actually multiply by. So here's a hint. What order would I love to have here? What am I in? I can transpose it. So what I'm gonna do is this. I'm gonna say A dot VI transpose. And now I don't have to do dot product. Now it's U minus AVI equals 0. So hopefully I didn't feel too like much of a cheat. Okay. Something we haven't necessarily talked about with vectors is that they are, I get distribution. So I'm going to actually do this distribution. I know this is true. This minus AVI transpose T AVI equals 0. Which means I'm allowed to do this. I can say for sure that this is true. AVI transpose U is equal to AVI transpose AVI. Questions so far? I really would like to solve for U. So that's the end goal here. And I think I'm going to fast forward a little bit because I'm running shorter on time than I wanted to. But basically, this is where we're marching toward. Here's how P and U are related in this hopefully not too strange combination of matrices. So remember, P again is some matrix or some vector in our span of A. U is just an arbitrary vector, doesn't have to be in the span. P is the vector that's closest to it. So this right here is another way to make that calculation if you don't feel like dealing with all those dot products. Now it's all collected in one calculation. How many vectors do I need here? Or sorry, how many matrices do I need to do this calculation? Huh? One. It's one matrix and a bunch of different manipulations of it. But as long as you define that one matrix from your calculator, you can transpose it, multiply it by other stuff, take the inverse of it, all that stuff. And you should be able to do it all at once, as long as you're careful about where the parentheses are placed and making sure that the calculations happen in the order you want them to happen. Go ahead.
And just to confirm, the U at the very end there is still going to be is still going to be to the dot product multiplication instead of reverse multiplication.
No, U is always a vector. Oh, wait, sorry, you're talking about this calculation here? There's no dot products in here.
And how are we going to multiply U?
Well, then that would mean that this dimension has to line up with that one, right?
Oh, all right.
You gotta make sure that's the case? Yeah. We can. It's worthwhile. What are the dimensions of A? Or what's the order of A? N by M. Is it N by M or N by N? N by N. So I told you it has N columns. I haven't told you how many rows it has, but it might not be the same. So we'll call it something different. If A is M by N, then what's the order of A transpose? Reverse them. Then what's the order of A transpose A? That's square, N by N. And if I invert it, what happens to the order? Nothing happens to the order. It should also be N by N. Okay, so now what I have is A, which is M by N. So A times, actually I can just do it here. A, which is how big? M by N. This whole inverse thing is N by N. And how big is A transpose? Or what's the order on A transpose? N by M. It'd be what? N by M? M, yeah, M twice, right? Mike by Mike. So multiplying all these things together gives me a square M by M matrix. How big is P? What's the order of P? Something by 1, right? So remember what P is. P is a linear combination of the columns in A, right? So how many coordinates do I need? So basically what A looks like is this, is column 1 is V1, then V2, all the way up to Vn. But for every one of these vectors, how many entries are in each one of these vectors? M. They go from 1 to M. So does it make sense that P is M by 1? Which means, and I said P and U, like, I can't say that P and U are close to each other if they don't even live in the same number of dimensions. So U would also have to be M by 1. So does multiplying an M by an M by 1 give what I care about? Okay. So yeah, you're right to be skeptical of it, because dot products, like, as long as they're the same length vector or same number of entries, that dot product works. You got to be so much more careful when you're doing matrices. But based on what we have here, and the fact that the only matrix fundamentally we're looking at here is A, aside from those two vectors. But all the orders should be fine. The only thing we really have to worry about is whether this inverse exists. So we'll talk more about that when we get into specific examples, which we don't have time for right now. So we'll talk more about that tomorrow, but we'll do a couple examples with that, and then we'll just to see how it works.